Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Alright, so this time I'm actually going to talk to you about a distributed system for a change. So this is a system called Naiad, which I'm currently working on with colleagues at MSR in Silicon Valley, Frank, Derek, Michael, and Martine. Okay, so what do I mean when I say data parallel? Very briefly, basically, a data parallel computation will express the program as a data flow graph. It will partition the data into many disjoint parts and spread these parts across processors. And then each processor applies the operators in the data flow graph to its part of the data. So what's appealing about these data parallel frameworks? Well, fundamentally, they hide the underlying complexity. They hide the complications of for the programmer of doing the parallelization, of dividing the data up into these chunks and distributing it across the machines, of scheduling the operations, of making sure that load is balanced, of recovering from failures, and so on. And most data parallel frameworks will offer some sort of higher level language support, so it's actually pretty easy for the programmer to use these things. However, as I'm going to show you, they do trade off flexibility for that ease of use. So the most sort of probably well-known example is MapReduce. And this was developed at Google for processing web data, and it was published at OSDI back in 2004. And since then, it's been picked up by an enormous number of people, and it's spawned this huge sort of research industry. So MapReduce, there's a very simple abstraction consisting of just two functional primitives. Firstly, there's a map stage, and here, this is where the operation is applied to the independent chunks of data, and the map will compute a set of intermediate key-value pairs, and then this is followed by a reduce phase, which combines the output of these map functions. And it basically applies a function to all values with the same key, so it combines the intermediate data generated by the map in the expected way. I'll show you an example. Word count, counting the number of times each word appears in a document, is a kind of classic MapReduce example that you see in many, many papers. So first of all, the input, the document or documents are partitioned up into disjoint partitions and spread across the processors. And then the map thing does the counting of the words that appear in each of these parts of the data. These outputs are then picked up by the reduce phase and combined. So all the results for the word apple will all be shuffled to the same reducer, and it will count all the occurrences of that. So this is a really simple way to program, but it's very restrictive. So first of all, the fact that it's fixed that there's only two possible stages, a map followed by a reduce, is pretty limiting. For example, in your program, you might want to have multiple map stages occurring one after another. You might want to chain lots of MapReduce computations together instead of having to, in its sort of purest form, the programmer would have to issue a separate job on the cluster for each MapReduce pair. There's also problems when you want to do something that needs to consume two inputs in parallel, like doing a join query. And also there's it's not able to produce two outputs of different types. And there's other issues as well. And the basic problem here is that the rigid semantics that are the abstraction that the programmer is dealing with are reflected in the underlying runtime system that's happening in parallel on the cluster. And it leads to lots of performance inefficiencies, such as unnecessary disk copies and network transfers. And if you want to develop a more complex program, it can be a challenge to make it work in this context. So the sort of next level of sophistication, if you like, is perhaps something like Dryad, which was developed at the lab where I now work. And this is a slightly more generalized framework. It allows an arbitrary number of inputs and outputs to each operator, and so the data flow graphs are more general, and they don't have to comprise this sequence of just map and reduce. So programs are represented as acyclic data flow graphs, and vertices are connected to each other by channels. And in theory, these are implemented in a number of different ways, but in fact, I've never seen a Dryad running that didn't use files. So the vertices in the data flow graph produce some data, write it to disk, and then the next vertex in the data flow graph will read that data from disk as its input and do its computation. And there's good language support for Dryad in the form of DryadLINQ, which basically turns declarative link expressions into a data flow graph. LINQ is a set of .NET constructs for dealing with collections of data for data sets. And these are LINQ queries are functional queries, so it's a bit like SQL. And it's embedded in .NET languages like C# or F#. Okay, so Dryad's more general than MapReduce, but there are still limitations. So it's designed for high throughput batch processing, which it does extremely well. It performs very well, but it does require that the data flow graph that gets scheduled for execution does not have any cycles, and also that the input data doesn't change. A lot of programs that people want to run in a data parallel fashion actually do contain iteration, and so this is a problem. The iteration part of the program is often a fixed point style of iteration that involving a convergence test, and so in this kind of batch processing environment, the convergence test has to be either run on the client, which means a Dryad job is sent to the cluster, processing happens, the results are sent back to the client checks whether it's done, and if not, it then issues a new Dryad job, which is not very satisfactory, because part of the point of these data parallel frameworks is that you can rely on them providing the fault tolerance, and this takes that away. Or else the client can say in advance how many iterations of this loop there are going to be, but that's also not satisfactory, because often the number of iterations is data dependent. And then since it's batch processing, obviously if the input changes, the whole job has to be rerun. Okay, so Naiad is taking this sort of series of data parallel frameworks one step further by supporting incremental update to the input and iteration. Sometimes we say we do this natively, and by that we mean we reflect the fact that our data flow graph can have cycles and can deal with the input changing in the way that the job is executed on the cluster. That will all become clear, I hope. So I'm going to start just by giving you an overview of Naiad and explaining how we program it. So as with every data parallel computing framework, the goals are to hide the complexity and to simplify the programming. And as I said, we also want to add expressibility. So we want to do incremental update, but we also have to do it efficiently, and we want to do this fixed point style of iteration. And in fact, being able to arbitrarily nest loops is also a very powerful feature of Naiad. So Naiad was originally sort of motivated by these observations about what actually happens in an iterative program. Often the state that's being iterated over actually doesn't change very much. And this means that it's possible to make the execution significantly more efficient by keeping state from the previous iteration around in memory. Secondly, as I said earlier, if the execution layer understands that we have loops in the dataflow graph, then we can push the convergence test into the computation itself, and the client doesn't need to worry about either doing the test itself or knowing how many iterations to do in advance. And another observation is that when the input actually changes, you know, if you imagine in a streaming setting, for example, you have new records appearing every so often, and often the impact of those records is only on a very small amount of the total computation. So it's not, you can get a huge efficiency gain by just rerunning exactly the part of the computation that is necessary. So Naiad is based on an execution model which we call differential data flow, and I'll explain what that is. Like DryadLINQ, it's a C# LINQ programming interface. It supports, as I said before, loops and incremental updates, and also prioritization of certain sets of records. And it does this in a fully composable way, so you don't have to say, I'll either do incremental update or I'll have some iteration. They both fit together very naturally. We've implemented it so that the same executable, the same code artifact runs on either a single machine, multi-core, or on a compute cluster. And in fact, when we run it on the cluster, on the individual nodes, since they're all multi-core, it's basically the same code. All the nodes in the cluster running a Naiad job are executing asynchronously. They're not, you know, there's no barrier synchronization. As I said before, it keeps the data resident in memory. So this is basically for efficiency when the loop is iterating, but it's also for efficiency when we're incrementally updating the computation. It isn't currently fault tolerant, but that's in the works. Okay, so let's start by looking at an example Naiad program. So this is some code to compute the connected components in a graph. And the first step is that the programmer has to write a C# program using the NaiadLINQ operators, which look an awful lot like LINQ operators. So what we're looking at here is let me explain it. So first of all, each node has its own ID, a label for itself. And then there's a fixed point loop where each node sends its label to its neighbors, and its neighbors send their labels to it, and then each node adopts the minimum of all the labels that it has received. And this keeps going until eventually there's all the nodes in the same connected component will have the same label. I've highlighted in yellow there the operator fixed point, which is something that we've introduced in Naiad. So this is not something that's in LINQ or anything else, and I'm going to talk more about that. So after the programmer writes this, the program is turned into a cyclic dataflow graph, which in this particular case happens to look somewhat like this. As you can see, there are various additional nodes that are introduced by the Naiad runtime. I'll talk about those. And it's, the structure of it is slightly obscure, but it doesn't really matter. Naiad deals with all this for us. And then this graph is constructed at some number of asynchronous workers. So by worker, I actually mean thread, but these threads, there can be multiple threads on each node in the cluster and then multiple computers in the cluster. So it's sort of irrelevant whether if I'm talking about two threads, whether they're on the same machine or on different machines. So the graph appears on all these workers. And effectively, what's happening with the data is that the state of each of these vertices in the graph, each of these operators is partitioned into what we call shards. And this is done by key. And each worker is responsible for one shard of every vertex. That's just some terminology that I'll be using later. And then in step 4, every one of these threads will proceed to execute the dataflow graph, keeping the state that all the input and intermediate state in local memory. So as the worker proceeds to execute the graph, it will generate records that have a different key to the key that it's wanting to execute on, and so the edges of the graph will basically turn into data exchanges quite often. So we deal with the fact that the input can change by introducing this concept called an epoch. So the programmer can update the input to a Naiad job by calling OnNext in the code to add a new bunch of records. So each of these updates is called an epoch. And the programmer will also register a callback for when the answer for each individual epoch is ready. As an optimization, the epochs can be overlapped. So again, it's a matter of the programmer specifying a window size. But even if we've got multiple epochs in flight at once, the results will get returned to the program in the right order, in the expected order. So just to sort of recap on what the system actually looks like, this is a kind of another view of it. So this is representing a single machine in the cluster, and we've got multiple of these worker things shown as horizontal grey rectangles. Each worker is executing a copy of the dataflow graph. They're all executing the same dataflow graph, and then each vertex inside that graph is split into multiple shards. So each worker is going to do the operation on its partition of the data. When a shard is finished running, there's this data exchange on a channel, and that channel on the same machine, it will be a shared memory buffer, and if it's going across the network, it will use TCP. And there's also a thing called a Naiad clock, which I'm going to talk about later. Okay, are there questions so far? Yeah.
The fixed point condition is implicit. This is the condition that when the state of the output doesn't change.
Yes. Yes.
Can you define your own conditions as
Not at the moment, but that's, yeah, that would be something that would be useful. I'll show you in more detail how fixed point works, and maybe it will become clear why we don't at the moment, but we would quite like to. I mean, you're talking about things like, you know, if two records are epsilon different, for example. Yeah, we don't currently support that. Okay, so I'm going to start by with the details of Naiad, just by talking about the incremental operators, how we define these data parallel operators that can deal with the input changing. Some more terminology. So, as always, computations are defined over collections of records, and these collections can vary with time. So each vertex stores a collection corresponding to every logical timestamp that that vertex is associated with. So starting from the input collection, basically the data flow graph is applications of the data parallel operators that the programmer has defined. So in Naiad, although operators are actually, sorry, Chandu?
So is this logical time advances when you say OnNext, or epoch and logical times are different?
They are different, but well, they're kind of different. Let me get to that. So in Naiad, an operation takes a collection as input and outputs a collection, and this is in contrast to, say, LINQ, for example, where for example, if you do a count in LINQ, the input will be a collection and the output will be a number. In Naiad, it's always collection to collection. But in fact, we don't work with collections in an actual Naiad program. What we work with is what we call differences. So a difference is a record, as you would have in a collection, a weight indicating how many copies of that record there are, and a logical timestamp. So if you have a record as input that has a +1 weight, it means that that record is being added to the collection. If the difference has a -1, it means that record is being removed from the collection. Okay, so this means that at any time, logical time in the program, a vertex just has to basically add up all of the differences in its state to turn that pile of differences into the actual collection. It turns out that this gives us some very significant efficiency gains, which I'll show you. So the Naiad operators that we've defined, this list is not actually covering all of them, but they're kind of the standard declarative operators, with the addition of fixed point and a couple of others that are more about housekeeping, so I'm not going to cover them in this talk. Okay, so let's see what happens when the input varies in a notional unary operator. So F is no particular operator, it's just a black box. So say we start at time 1 with an input X. Okay, so this will result in F being applied to X and the output. Now let's say at time 2, delta is added to the collection. Okay, so now the vertex, the operator F, has to output F applied to X plus delta, and it also has to rescind the F of X output that it produced in the previous timestamp. And say at time 3, we've got epsilon added to the collection as well. Again, F is applied to X plus delta plus epsilon, and the result from the previous execution has to be rescinded. So this seems a very, to add a lot of complication, but actually it's not too bad because many of the operators are linear, and we can leverage this to make this execute quite efficiently. It's actually not a problem. The fixed point operator is slightly different to all of the other operators, which behave somewhat like the example I just gave. So fixed point is actually a subgraph of its own. It's not a single vertex. And it consists of an ingress node, the fixed point operation, again, it's labeled F here, the egress node, and something along the back edge of the loop that we call the incrementer. So when a record arrives at the input of the fixed point subgraph, basically we're keeping track of which iteration that record belongs to in the loop. And this is done by the ingress operator, which just adds a time coordinate. Every time a record goes back around the loop, that time coordinate gets incremented. And then at the egress of the loop, when things have converged, which I will explain later how that works, the egress is stripping off the time coordinate and also consolidating all of the records that have been produced along the way and outputting the answer, in this case, Dave at 37. So how do we detect convergence? As you asked earlier, Kapil. So the naive solution, store the complete result and from the previous iteration compare with the current result. Okay. Better solution is to have some kind of distance metric between these two. What Naiad does is that every time an input arrives at the fixed point, the ingress operator adds the iteration number to the timestamp, as you see there, x at I0. And it also emits the rescinding of x for the next iteration of the loop. And because the incrementer accumulates records at every timestamp, these cancel out. And when no more records are produced, then the iteration terminates. I'll show you a picture of that, which will make that clearer. Okay. So if x at time I appears, the ingress vertex will emit x at time I with the loop iteration number appended to the timestamp. It will also emit negative x. In fact, it will emit negative x at time I1, but I've just put it the other side of the incrementer because it makes the picture clearer, and you will see why in a second. But that's basically what's happening. So records are scheduled in time order, so inside the fixed point subgraph. So we're going to see f, first of all, applied to x at I0. So we get f of x output there, and in fact we get it copied both to the output edge and to the back edge of the loop. The incrementer then increments the timestamps of both of these things and produces f of x minus x. And this goes around and becomes the new input. So notice here that we've now got x plus f of x minus x. So x minus x makes x go away, and so the input to the second iteration of the loop is now f of x, which is exactly what you would expect. So when f of x is the input to f, we've now got f applied to f of x, and again the negation for the following iteration is issued, and so it continues. f cubed of x, etc. And then finally, all of these, the records, the outputs that are sitting there at the egress are consolidated. They're all added up, and the result is going to be the fixed point. Is that does that make sense? Yeah. Iterative computation. So that's a good point, actually, because as you can see, it's basically making use of the fact that of the way that we do incremental update. So it's a combination of both iteration and incremental update. But its primary purpose, I suppose, is just a loop. But it absolutely, yes, that's right. Okay. Okay. So that's a brief overview of the operators. I mentioned at the beginning that Naiad has this differential data flow computational model, and what I'm getting into here is this business of logical timestamps and how that helps us. Okay, so assume we have an operator taking a collection labeled X and turning it into a collection labeled Y. I've already explained to you how we actually work with differences rather than with collections. So it's a record and a weight or a delta for each record. In this little visualization, I'm going to sort of highlight with a purple box the which of these differences I'm referring to as I'm talking. Okay, so some new differences arrive. They get processed by the operator and output, and in fact we can define those differences in terms of their difference from the previous one that we saw. So another set come, and these are defined relative to the previous inputs, and the output is the difference from the previous outputs, and so on. Okay. In fact, this is basically logical time. You know, we're saying that the differences at step 1 or the differences at step 2 are relative to the differences at step 1, and so on. Nothing particularly surprising there. However, what if we now get a new version of the input that we saw at step 1 previously? You know, what if we want to make a slight change to that input? Chances are we can actually define the differences, the input and output differences here, relative to the differences that we had at the same step of the computation for the previous version. Another one comes along, and now we've got two places where we can define that these differences can be defined as different to the previous version, the same step of the previous version, and the same version but the previous time in, or operation in the horizontal sense. And this can just continue. So basically we've got this notion of a difference being defined in terms of two time axes, and there's actually no reason why it has to be just two. It can be as many as you want. Effectively, what we're defining here is time, logical time, as being a partial order. So thinking back to the fixed point operator that I showed you before, where you might say that these horizontal differences, maybe these are differences where the loop counter is being incremented, and each difference is relative to the previous loop iteration, and then the vertical ones might be versions of the actual input, for example. So in the way that it's implemented, a timestamp is just a tuple of integers. Somebody asked me about epochs earlier. Was that you, Chandu? So the epoch that the input belongs to is always the first entry in this tuple, and then subsequent loops add new dimensions, add extra dimensions, which is how we are able to arbitrarily compose. We're able to nest loop iterations. And as I explained when I gave you the definition of collections and differences, the collections at any time t are the accumulation of all preceding differences, but now we have this partial order-based definition, which means we can define those differences relative to the differences, above us in the grid, or to the left of us in the grid, which corresponds to perhaps the previous iteration or the same iteration on the previous version. And in practice, this really does result in some good efficiencies. Here's an illustration. So this is running the Connected Components program that I showed you at the beginning. We're running it on a network of about 400,000 nodes and 3.4 million edges, it's actually one of these downloadable things. It's the Amazon Product Co-Purchasing Network from June 2003. So on the x-axis, I'm showing the round of computation, or the iteration number. The y-axis is the value normalized to the first iteration. So, and then the other y-axis is the cumulative wall clock time, which goes from 0 to 250 seconds. So if we look at the red line, the one that shoots up to 2, that's the number, a count of the number of differences being processed. And you can see that it shoots up to 2 because that fixed point iteration is producing a whole load of negative differences. And so effectively we get twice as many records, but then the number that have to be processed drops off pretty sharply. The blue line, the one going up, the diagonally up from the left there, is the actual processing time. So after round 15, we've taken 220 seconds or something like that, but the remaining 20 rounds of computation take almost no time. And the time per iteration is the green line. So again, it drops off pretty sharply after about 10 iterations. The green line is relative to the value, to the normalized first iteration. And so what this is showing is that computing this loop accelerates as we get closer to converging. And then what about the incremental update? Well, here's a result from a multi-core machine. This is running single source shortest paths on a 1 million node graph, a synthetic graph, and there are 10 edges per node. So the top graph here is showing what happens when we've got 48 workers, 48 threads, and the bottom is just one worker. And we've got, it's a CDF where the left is the percentage of updates, of incremental updates that are completed, and that y-axis on the right is spurious. That shouldn't be there. So the bottom is the time in microseconds, and it's in log scale. Okay. So what we're seeing is it's basically showing us two things. One is the speed of incremental update compared to doing a full recompute. The dashed grey line over to the right is how long it takes to completely recompute the answer with the new input. So obviously we win almost all of the time. There's a bit of a tail there with 48 threads, but most of the time it works well. The 3 lines are for different batch sizes. So when the batch size is 1, it means we're 1 edge at a time in this 1 million node graph, or 10 million edge graph is being updated, and then we're going off and recomputing the shortest paths. So in this case, with 48 threads, this is the leftmost line, it's actually slower than with 1 thread, and this is because there are coordination overheads. But as the batch size increases, we actually get much better performance, as you would expect with more parallelism. Okay, so I'm now going to move to, maybe I should pause there. Are there any more questions? Yeah. Could you repeat that, please? The in-memory, having to keep the state in memory is, certainly it does give us a huge performance advantage. It's not strictly necessary to be able to do incremental update. We could flush state to disk and page it back in when we need it. At this clock protocol that I'm going to talk about gives us a way of doing that sensibly, given that we know the structure of the data flow graph, so we could flush when we know we're not going to need that state anymore. Obviously this is a limitation of Naiad, though. The fact that we do need state in memory to get good performance means we're not going to be doing processing over massive amounts of data. But on the other hand, because we have the state in memory, we can do this incremental update really fast, and so it's a trade-off. Yeah, there are special cases. We can talk about that later. Yeah, but yeah, you're right. Okay. Yeah. At the moment, the programmer has to do it. That's, again, something else that we need to make more user-friendly. But it's just a hash partition. It's just based on a key. But it is, you have to write a program to get your data file, to get your partition files on the spread out across the cluster. Yeah. Yeah. The priority. Do you mean priority of the operators or of the data? So actually we do that just by adding an element to the timestamp, in fact. So if we give, if we put our records into buckets, where the buckets are ordered by the priority, and we give all the ones in, bucket 0 timestamp, their second element in their timestamp 0, then those will all get processed before the ones with the element 1 in their timestamp, and so on. So it's actually quite a simple thing to do in this framework.
even after the computation is over, something like forward error?
So the
Because I mean, while the computation is going on at that time, getting new set of records is, I mean, that assumption is not very, useful, because otherwise you would have put that record in your file itself and then you would have circulated that. Say if you are indexing your web pages, and you have a certain, you have already indexed your web pages, and then you have some changes in your some of set of web pages, and then you have to recompute that to the. How do you do it?
I'm actually going to talk about that with this clock protocol. I mean, what you're asking is, how do we know when an epoch is finished? And we have the answer, right?
No, what I'm saying is, like, see, in this case, that you can add, when can you add new data? That is what, that is the first thing.
You can add new records anytime.
That is what I mean. Even after the computation is over and you have all the results that out has churned out all the results.
There's a difference between finishing an epoch, saying, okay, here are all my records for now, and saying computation is finished. So you can keep the computation alive, keep the state in memory, and then just introduce new records in a new epoch as and when they arrive.
So are you familiar with partitioning?
Yes.
So in that way, they are storing the intermediate math, right?
Yeah.
So in that case, even after your reduces are over and everything is gone, so they can retrieve those maths and again do.
Okay. Yeah, we don't do any kind of checkpointing at the moment. This is obviously something that we're going to have to do to introduce fault tolerance here, and maybe we could also use it to do something like what you suggest. But I mean, it's certainly, if you're doing any really long-running large data computation, you certainly would want to do that, I think. But we don't at the moment. Okay, so the distributed clock protocol. So when we moved from the same machine multi-core version, which was the first, the way we started running Naiad, initially we moved to running on the cluster, and we realized that we had some serious challenges, in particular to do with resource management. Part of the problem is because the fixed point computations accelerate as they get nearer convergence, we end up with lots of shards having very, very small number of records to process, and they actually run for a really short time. And frequently, shards don't have any records to process at all, and so they don't even get scheduled. And this is a challenge for the coordination of the job globally. As you've already gathered, memory management is a real issue here. Choosing the best shard or vertex to schedule next on each machine individually. All this stuff has to be done locally, and it has to be done in a way that won't exhaust the resources available and will also give us good performance. And fundamentally, this boils down to one thing, the bottom point there. Threads need to know which of their vertex versions may still receive updates. So by version here, I'm talking about a particular vertex or shard at a particular logical timestamp. So this hinges on this notion of reachability. So what we need to do is define a partial ordering of these vertex versions. So we say that a version V is reachable from U if executing U could possibly produce an output for V. And we write it like this. It's like vertex U at timestamp I, TI, the other way around. V at TJ is reachable from U at TI if when we run U at time TI, there might be records, differences produced for V at time TJ. So computing this is actually really simple when you because we know the data flow graph structure. I won't go into it. And also because our logical timestamps have a lexicographic ordering. So the Naiad clock is a distributed protocol which is tracking globally the number of outstanding differences for each version in the data flow graph. And the way that it works, it's actually really simple. A vertex runs, it then broadcasts the number of differences it produced, and then it broadcasts the number of differences it consumed. So let me show you an example. So if we have as input to vertex A here a difference x at time ij, and it has a weight of +1. Let's say that A produces two records as output, two differences as output. One is a +1 for y, and another is a -1 for z, saying that z is being removed from the collection. And these outputs get sent on to on edges towards vertices B and C. Then A will broadcast a clock message saying +2, the two differences. Okay, one is a removal of a record, but there's two differences there. So +2 records for B, +2 for C, and I've consumed one, so -1 for my version. And then every worker keeps what we call a version count set, which looks like this thing on the right. So there's the version. Vertex U at time ti has, say, 6 outstanding differences somewhere in the system. And V has 14 and W has 1. And what this means is that if you have a version that's not reachable according to that reachability relation I defined earlier, then we know that no more updates exist for this version. It's not going to receive any more updates ever in the future. So the clock is actually just a summary of the VCS for each worker, and it keeps the versions that are not reachable from any other version of the VCS. So you could think of that as the base set. Yeah. So it's both, because we know the structure of the data flow graph, so we know if there's an edge or a path from U to V, and then if they're not, if they're like inside a loop, we can look at the lexicographic ordering of the timestamp to see which one was executed or before the other. Okay, so the clock, you could think of it as it's like sweeping up behind the computation. It's basically giving an indication globally of how far through the data flow the computation has become. Have to remember that this is actually quite complicated to work out by other means, because although the data flow graph is the same on every vertex, one worker is not necessarily scheduling the same version to be run as another, so two different threads can be doing completely different things. So the clock also shows us when a computation is complete. So when the clock is empty, that means there are no more records to be processed and we're done. The way it's initialized is that the number of inputs causes the version counts to be initialized before the computation begins. And we change epochs by broadcasting a positive clock message for the new epoch followed by a negative message for the previous. Has some really nice properties in the distributed setting. It's completely decentralized. There's no need for any synchronization between workers in order to figure out what the clock is, which vertex versions might still get some inputs. It does assume that messages are FIFO, however. It decouples control plane and data planes, so this means that we can vary how often we send clock messages so that we can trade off between having the most up-to-date information about the clock, or if there's too much clock traffic that's sort of overwhelming, that's dominating the network traffic, we might want to back off, and then everything will still be correct. We just won't have necessarily the most up-to-date information about the clock. And the workers only need to send clock messages when they've actually done something. So it's not a case of having rounds where everybody has to send each other a message to say what they did. It's only necessary to send a clock message when a record has been consumed, a difference has been consumed or produced. So uses of the clock. Scheduling is one place where we use it. There are sort of two styles of scheduling. Conservative, it's just a question of picking a vertex whose version is in the clock, because now, by definition of the clock, this means that all the inputs for that vertex are going to be available. And we can vary how we choose from among that set a little, depending on policy. So the oldest timestamps favors latency. It means a result will appear as soon as possible, and but choosing any version will favor throughput. Alternatively, scheduling can be speculative, which means scheduling vertices that are not in the clock. And we can actually get away with this here because of the incremental computation model. All we need to do is, if we generate incorrect outputs because we've run without waiting for all the inputs, we just have to retract them again. So we've tried this, and it's actually really hard, and we had to turn it off because it made our performance terrible. So this is a speculative execution is a work in progress, but it should be possible to do something here that might help performance. Other uses that I'm not going to talk about in any detail today. Memory management. We know when an epoch is done, even with certain vertices, and so we can go in and compact the memory and reduce the footprint, and that actually has a significant positive effect on our memory footprint in practice. And we can also use the clock to tell us when an epoch is completed, and then only output the results when the epoch is finished, even though there might be multiple epochs in flight at once. So finally, in the last 4 minutes, I'll just show you very briefly some actual experimental results. So we have a cluster of 16 servers. We looked at 3 classes of application. I'm only going to show you 2, the batch iterative and incremental iterative. So here we looked at 3 algorithms, PageRank, strongly connected components, which is a very challenging algorithm for these types of systems because it actually has a doubly nested loop. It calls connected components twice inside its main loop and connected components. And we ran this over a publicly available data set of 50 million web pages. So we didn't do the comparison. We took this from a paper that somebody else published, but they ran these algorithms on the same hardware using using Parallel Data Warehouse, which is a Microsoft product, and DryadLINQ. Naiad actually did somewhat better than all the other systems for these 3 algorithms. SCC, we thought we'd get a much greater win, but in fact the other systems didn't run strongly connected components on their cluster. They used the cluster to trim the graph, so they removed the nodes with no in or out links, and then they ran SCC on a single machine because that was the only way that they could get it to run in any sensible time, whereas Naiad just ran the whole thing on the cluster. Also worth noting is that although this is an experiment looking at batch processing times, Naiad is of course primed and ready to do incremental updates on any of these inputs, whereas these other systems would have to rerun from scratch. And then finally, we looked at finding the strongly connected components inside a Twitter graph. We took a month of tweets, worked out to around 2,000 tweets per second. And in this experiment, we had a sliding window of 24 hours. So 24 hours, the strongly connected component structure inside each 24 hours. And we advanced it in different increments. So essentially, we were doing incremental update with different batch sizes. And we preloaded the first day of tweets. So looking at the update latency, this is a log scale x-axis, and it's the time to process each batch in seconds, going from 0.1 up to 100. And then on the y-axis, this is a CDF. We've got the fraction of batches processed. So the leftmost line is a 1 second batch size, and we can do almost all, but not quite, of the batches in under a second. So we're almost real time where we do this every second. Things get better as we increase the batch size. So for example, if the batch size is 100 seconds worth of tweets, then we're able to do to update the graph, the strongly connected components graph, in less than 10 seconds. So we're pretty happy with these performance numbers. So in conclusion, we've got a bunch of ongoing research. We don't have any papers on this yet. We're looking at introducing fault tolerance. The clock gives us a really nice framework for doing that, as I mentioned before. Our memory management it's still pretty challenging. Another interesting research topic is dynamic repartitioning. Moving, introducing or taking away shards according to where we are with respect to load balancing. Martine is working on a correctness proof of the clock protocol, and we're really serious about trying to get some, I'd say, real users in quotes, because if we can get some researchers in our lab to start using Naiad for their research, then that would be a great start. Any more questions? Okay, thank you.